Good evening. Today I will introduce to you the concept of kinematics. Kinematics is a concept which is used in mechanisms design, the way mechanisms work, in machines, system linkages, robots. I'll explain to you that first of all, imagine this is one of those cranes there that you have there and that is working. So this is a mechanism, this is a system, and it could even be robotized. And this does a certain task, which is moving around and allowing the end effector here. The end effector is being defined at the point where there is a task which is being performed. Then what you have here is you have an actuator here, a cylinder, you have an electrical motor here, or perhaps another type of motor, diesel operated there, which is going to turn it around. It's going to be moved this way by this actuator, and this is going to be telescopically moved towards this position here. And you will also have a position that will be changed of this hook there through a winch here. So you have different actuators which are actually operating this end effector. The same can be said about this other mechanism, which could also be a robot, is it's a lift platform. So what you have is you have an interest in the height of this, and you have multi-linkages, and if you turn it this way, in this case, which would be the actuator, in my case it's manual, but I could replace that easily with a motor, an electrical motor or any kind of motor. So I can change the height of this platform by turning this knob here, which would be the actuator. So the end effector will be something sitting on the platform, or the platform itself would be the end effector. So now, and you can imagine all kinds of robots, and you can portray these things, and as a homework you can sketch a few robots, make a few pictures at home and bring them back to me and show these concepts there, explain these concepts from different robots that you can find on the internet. Okay, so that would be your homework for the next time. So now that we have the linkage defined, so the linkage is described by the length of its bars, the width of its bars, and perhaps also another width here, okay, or a breadth. All of that will describe the specificity of that mechanism, of that machine there. So we call that the configuration values, those lengths, those widths, those thicknesses, all these kinds of things which describe this specific. We can make it bigger, we can make it smaller. Anyhow, it's the same mechanism, but the configuration parameters define it in its geometry. It defines it to be of that kind. That's very important to describe that when you specify a machine in kinematics. Then you have your actuator. So your actuator is actually turning this knob, this angle, with this screw there. It's going to change the distance between these two bars here. And it's going to define, by moving the distance of these two bars, changing that distance there, it's going to define the height there. But the height does not really, it's not easy calculated from the turn knob here, that angle here, okay, that rotation here. So this is what we control. A controller, if it would be a robot, would be working with this, with a sensor, and would just turn it around, or myself, I am doing the control at the moment. So I'm doing the control and I'm turning it. But what I'm interested in is what happens here. It's a height. This is what is of interest. This is the task. And the same here. With this crane there, what is interesting is where is this hook? So we can manipulate something and lift some goods and transport them around. So we need to determine what's happening with the winch. The motor is there. We need to determine what the extension there. So we have some lengths here. And we are going to change the angle of that boom, which means that we are interested in the length of that hydraulic actuator which is actually operating it, and we need the angle of rotation of that truck there. So in this sense, and we can even imagine if it's a mobile vehicle, then, well, in this case, we are going to go around. We're going to be, as a non-holonomic vehicle, we're going to go around somewhere with this. So we have a bunch of actuators which are going to define the hook position of interest, the task here. But the actuators are controlled. So we're working on the controls. The guy who's in there, or the controller, or anyhow, is actually playing with these actuators. But what he wants is what is going on here. If it's a guy who's going to use his vision system, so it's going to be the measuring there, and is going to make the relationship in our brain, it's extremely complex. The non-linear approach there is going to be handled there. So how do we define that? Kinematics is an implicit relationship between those parameters, the configurations, the n effector pose, which is described by position and orientation in space, for example, 3 angles, 3 positions, translations there, and then the actuators. So it's a function between those two going equal to 0, and it's a non-linear equation system there. Most of the time, like this, or most of the robots, except for Cartesian robots, which we have seen in the course last week, it goes to a function. It goes to a function which is not necessarily easy. And then we can describe in modeling 3 types of models: the forward kinematics problem, the inverse kinematics problem, and the calibration problem. The forward kinematics problem is simple. It's given the position of the actuators, give me the end effector position or pose with the orientation. So that's a forward kinematics problem. In an articulated robot, for example, which is serial, like our arm, it's straightforward, it's explicit. However, if I do the inverse, it's not. I can, with an arm, I can pose it differently to get the same position, because I have a lot of degrees of freedom, as we've seen, okay, in another course. So because we have a lot of degrees of freedom, we can pose it differently. The inverse kinematics problem has many solutions. It has an equation system, a nonlinear equation system, which has many solutions there. The one which is forward has 1 or 2, sometimes 2, but it's the same solution, like 1 is plus, 1 is minus often, okay? So, and it's easy to solve. The negative one doesn't exist, okay? So now, in the case of calibration problem, is I give you these positions, I give you the end effector pose by measuring it, so I put the robot in many different positions there, pose, and try to calculate the lengths. Try to calculate the dimensions of the configurations from that. So it's an optimization problem because you have a lot of solutions there, and you're trying to calibrate. You try to determine exactly the positions of your machine there. Solving it, well, once you have the models, because it's a model of a physical system which is actually geometric, so it's not even physical in the sense that we take care of the weights, the masses, and all these kinds of things. We are not taking care of the forces. We are in geometry only. It's a kinematics, so we are just thinking about distances, okay? So we have a nonlinear equation systems. If we have an explicit equation, it's easy. We just calculate. If it's not explicit, the solutions, then we have to use a numeric methods like the Newton method, or we can use also algebraic methods, which has like the Grobler bases, which gives you an exact solution, but it is lengthy. The numeric methods are iterative. They find a solution very quickly, but you're not sure of which solutions, and you may not find one. Thank you.